Hey everyone, if I come off as a little bit peeved, I am. I just finished this video and uh, had my screencast program freeze like right as I was ending the recording. So 30 minutes of my life down the toilet. So anyways, we'll try again. Take two. I had a perfect take one, so hopefully I don't make any mistakes on take two. Okay, so section 6.5 deals with average value of a function. This lesson here is a really easy one. It's like we're not really learning anything new in this section. The big key for what we're learning here is being able to determine when a problem asks you for average value or average rate of change. And you guys will see with the rates problems that we start to look at this upcoming week, and I think their rates problems are the hardest free response type question in the Calc AB class. You guys will see this topic come up in those types of questions. So we'll talk about like some things that you'll need to understand well to know what you're doing with the rates problems at the very end of the lesson. Okay, so let's get into the average value of a function and how we find it. So it says if f is integrable. So that's a new term. Differentiable means that like the derivative exists at a certain point or on an interval. Integrable means the same thing. So if it says that if f is integrable on the closed interval from a to b, that means that you can evaluate that integral on the closed interval from a to b. Then its average or mean value on the closed interval from a to b is given by this equation, okay? So f sub av, the average value of f is going to be 1 over b minus a. So we're taking 1 over the length of our interval from a to b of the integral from a to b of the function f of x, which we're integrating with respect to x. So the only new thing we're doing is we are dividing our integral by b minus a, or multiplying it by 1 over b minus a. Okay, and then the second thing you're going to need to know for this lesson is the mean value theorem for definite integrals, which says that if f is continuous on the closed interval from a to b, then at some point c, on the closed interval from a to b, f of c has to be equal to 1 over b minus a times the integral from a to b of the function f of x, which you're integrating with respect to x. So what that's saying is that if your function is continuous on a closed interval, there has to be some point on that interval where the function value at that point is going to be equal to the average value of the function on the given interval. Okay, so we're going to take a look at two examples here involving this. So the directions for the first ask us to find the average value of the function f of x, which is equal to 4 minus x squared on the closed interval from 0 to 3. And then does f take on this value at some point on the given interval? And the last part asks us to find c. Okay, so first thing we want to do here is calculate the average value. So f sub av is going to be equal to 1 over the length of our interval, which is the ending point 3 minus the starting point 0, times the integral from 0 to 3 of the function f of x, which is 4 minus x squared, which we are integrating with respect to x. So really easy integral for us to evaluate. So that's going to be 1/3 times, and then we can go ahead and take the antiderivative of the function the way that it's written. So the antiderivative of 4 is 4x, minus the antiderivative of x squared is x cubed over 3, and then we're going to evaluate that at our limits of integration. So f sub av is going to be 1/3 times, when I evaluate my antiderivative at 3, 4 times 3 is 12. minus 3 cubed, which is 27, divided by 9, or sorry, divided by 3, which is 9, minus, and then when we evaluate at 0, we get 0 minus 0. So f sub AV is going to be 1/3 times 3, which makes f sub AV equal to 1. Okay, so that takes care of the first part. Second part, does f take on this value at some point on the given interval? And the answer there is yes. The thing that we have to check for here is that our function is continuous on the closed interval from 0 to 3. Well, the easiest and quickest way to check for continuity on an interval is to find the domain of your function on the given interval. Okay, so because f is a polynomial function, it's defined everywhere, thereby making it defined on the closed interval from 0 to 3, and therefore it is continuous on that closed interval from 0 to 3. Okay, the third part says to find c. So what that's asking us to do is we're asked to find the value where our function is going to be equal to the average value on the closed interval from 0 to 3. So what we're going to do is we're going to set our function 4 minus x squared equal to the average value, which is 1. Now, I'm not going to find c, like actually find the variable c, but when it says find c, we're trying to find the x value on the interval from 0 to 3 for which that occurs. Okay, so I can go ahead and subtract 1 on both sides and add x squared to both sides. So that happens where x squared is equal to 3. I then take the square root of both sides, which gives me the absolute value of x equal to rad 3, which makes x equal to plus or minus rad 3. Now, both of the solutions don't work in this instance. We only want to find the solution that is on the closed interval from 0 to 3. Okay, and that's going to be x is equal to rad 3. Okay, so that right there is our c value for that first example. Okay, let's move on to the next one. So the directions here say to find the average value of the function on the given interval. Okay, so we're given the function g of x equal to x squared times the square root of 1 plus x cubed. And we're looking at that on the closed interval from 0 to 2. Okay, and then we're also asked to find x such that the average value of g is equal to g of x on the closed interval from 0 to 2. So I'm going to have you guys work this one out on your own. So to do the first part, to find the average value, you can do that by hand. To do the second part, you're going to need your calculator for the second part. Okay, so go ahead and give that one a try, and then I'll work on it with you guys. Okay, so let's take a look at this one. If we want to calculate the average value of g, that's going to be g sub AV, which is going to be 1 over the length of our interval, 2 minus 0, times the integral from 0 to 2 of our function x squared times rad 1 plus x cubed, which we're integrating with respect to x. Okay, so for us to evaluate this integral here, we're going to have to do a u substitution. So I'm going to let u equal the inner function in the composition, 1 plus x cubed, which is going to make du equal to 3x squared dx, and dx equal to du over 3x squared. Okay, so that's going to make g sub AV equal to 1/2 times the integral from, now I'm going to change, because I'm trying to get my integral written in terms of u and du only, I want my limits of integration written in terms of u as well. So when I plug the upper limit in the place of x, that's going to be 2 cubed plus 1. That's going to make the upper limit in terms of u 9. And when I plug the lower limit 0 in the place of x, 0 cubed is 0 plus 1 is going to make the lower limit 1. Okay, and then my function is going to be x squared times rad u, and then we're going to replace dx with du over 3x squared. So the x squareds cancel. I can pull 1/3 out front. So g sub av is going to be equal to 1/6 times the integral from 1 to 9 of rad u du. So we have our integral written in terms of u and du, which is what we want. Okay, so I can go ahead and take the antiderivative. So antiderivative of u to the 1/2 power is u to the 3/2 divided by 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. And then we're going to evaluate that at 9 and 1. 1/6 times 2/3 is going to be 1/9. 9 to the 3/2 power is going to be the square root of 9, which is 3, cubed, which is 27, minus 1 to the 3/2 power is going to be 1. So that makes the average value of g equal to 26 over 9. Okay, and then we're asked to find x such that the average value of g is equal to g of x. Well, we first want to make sure that we can determine that. So when I look at the function g on the closed interval from 0 to 2, the only values we have to worry about are those values which are going to make the argument of the radical negative, because I can't take the square root of a negative number. Well, if we take a look at every value between 0 and 2, the argument of the radical for all of those values are going to be positive, which makes the function defined on that closed interval from 0 to 2, thereby making it continuous on that closed interval from 0 to 2. Okay, so there has to be some point where the function is equal to its average value. So we're going to set the function x squared times rad 1 plus x cubed equal to the average value 26 over 9. And you're going to need your calculator to do this. Now, there are two ways that you can do this on your calculator. If you have a more recent calculator, there should be a solver on your calculator where you can input the function, set it equal to 26 over 9, and that'll give you the values for which that will occur. Okay, so you can use your solver to determine that. The way I would actually do this on my calculator, because I didn't have like a solver whenever I was learning this in high school. So what I would do instead is I would input my function in for y sub 1 and 26 over 9 in for y sub 2. And then I'd want to determine the intersection point of those two graphs. Now, when you make your viewing window, you're going to want to make the x values between 0 and 2, because the c value that you're trying to calculate has to be on the interval from 0 to 2. And then if we're trying to find the intersection point, we're trying to find where that function is equal to 26 over 9. I'm going to want to make my window around the y values of 26 over 9. Okay, so I would want to make like a viewing window where I could view 26 over 9, which is a little bit less than 3. I'd want to be able to view that on my window. So you would just input that in for y sub 1 and y sub 2, and then calculate the intersection point of those two graphs. And when you do so rounded to 3 decimal places, that's going to be approximately, x is approximately equal to 1.281. Okay, so that's going to be the value for which the function is equal to the average value. Okay, now I want to talk really briefly on what happens whenever we take derivatives and integrals of functions. Okay, because we're going to need to understand this really well for rates problems. And then we'll get into how can we tell whether a question is asking us to determine average value of a function or average rate of change. Okay, so let's say we are given a position function, s of t, and then we're asked to find the derivative with respect to t of that function. Okay, so we should know that when we take the derivative of a position function, that is going to give us the velocity function. Okay, now let's say position is measured in terms of meters and time is measured in terms of seconds. Okay, So when we take the derivative of position, that gives us velocity. So we know our unit of measure for velocity is going to be meters per second. Now, the reason that that unit looks like so is one of the ways that we can take the derivative with respect to t of the position function is to write it in this notation. Okay, ds over dt. And if you guys remember back to related rates, like the form of your derivative is going to dictate what the unit of measure for that derivative is going to be. So the unit of measure of the numerator, s, is going to be measured in terms of meters, and the unit of measure of the denominator, time, is measured in terms of seconds. So that's why when we differentiate position, our resulting unit is going to be meters per second. And we can do the same thing when we differentiate velocity. We know the derivative of velocity is going to be acceleration. And the unit of measure for acceleration in this particular case would be meters per second squared. Well, the reason the unit of measure is meters per second squared is I can write the derivative of the velocity function as dv dt. The unit of measure for velocity is going to be meters per second divided by the unit of measure of time, which is in terms of seconds. So that's going to be meters per second, or meters per second squared. Okay, so what that tells me is anytime I take the derivative of a function, whatever I am taking the derivative with respect to, okay, so for both of these, I took the derivative with respect to time. I am going to be adding a unit of measure of time into my denominator each time I take a derivative. And that's going to be true for any rates problem. Okay, so whatever variable you're taking the derivative with respect to, you're adding the unit for that variable into your denominator. Now let's take a look at what happens whenever we integrate. So let's say we take the integral from a to b of the velocity function. So if you guys were to picture this really quick, let's say you have a velocity function, and then that's going to be your t-axis. If we were using like a Riemann sum to estimate the area, if we wanted to find the area of that rectangle, the base of that rectangle is going to be some unit of measure of time, which is going to be in terms of seconds. And the height of the rectangle is going to be written in terms of meters per second. So when we find area between the velocity function and the t-axis, the resulting unit is going to be seconds times meters per second, which is going to give us a resulting unit which is written in terms of meters. And we know enough about integrating that if we use part 2 of the fundamental theorem of calculus, we can take the antiderivative of our function, evaluate it at the upper limit, minus the antiderivative of the function evaluated at the lower limit, and s of b minus s of a gives us a displacement on the closed interval from a to b. So displacement is the change in position. Now, the way I like to think of this is whenever I integrate a function, the unit that is going to result is going to be the unit of measure of the function that we are integrating times the unit of measure of the variable that we are integrating with respect to. So the unit of measure for velocity would be meters per second. I multiply that by the unit of measure for time, which is in terms of seconds. So the resulting unit of measure whenever we integrate is going to be written in terms of meters. Okay, same thing for the acceleration function. If I want to see the resulting unit whenever I take the integral of acceleration, the unit of measure for acceleration would be meters per second squared. The unit of measure of time is going to be seconds. So when I multiply those two units, that gives me a unit of measure of meters per second. And that makes sense because when we integrate the acceleration function, that's going to be the velocity at the upper limit minus the velocity at the lower limit. So that's v of b minus v of a. and the change in velocity is going to be measured in terms of meters per second. So the big key with the rates problems, and what makes them really difficult, is you have to be able to look at a word problem and the function that you're given, and then determine the function that you're trying to find. Like, do I have to take the derivative to find that function, or do I have to take the integral to find that function? And for me, the way I determine that a lot of the times is I look at the unit of measure for the function that I'm given, and then I look at the unit of measure for the function that I'm trying to find. If I am adding a unit in the denominator, that means I'm going to be taking a derivative. If I am getting rid of a unit in the denominator, that means I'm going to be integrating. Okay, so that's something really important to keep in mind with the rates problems that we're going to look at this week. Okay, now, last order of business. And this is going to be what makes average value challenging, okay, is figuring out, is the problem asking me to find average value, or is it asking me to find average rate of change? Because the formulas for those two things are different, okay? So again, I'm going to take motion because those are the rates that you're most familiar with, but this is going to apply to any rates problem, okay? So if you're given the position function, x of t, and you're asked to find average velocity on the closed interval from a to b, and you want to determine if you're being asked to find average value or average rate of change, you have to compare the function that you're given to the function that you're trying to find the average of. Okay, so if we're given position and we're asked to find average velocity, we know velocity is the rate of change of position. So this is asking us to find average rate of change, which would be the position at our ending time minus the position at our starting time over our ending time minus our starting time. And that is going to give me an average velocity, because the unit of measure in your numerator would be a distance, which we'll say is in terms of meters. And the unit of measure in your denominator, those are times, which are written in terms of seconds. The resulting unit there is going to be meters per second. Okay, if we're given the velocity function and asked to find average velocity on the closed interval from a to b, how does our function relate to the function that we're trying to find? If we're given velocity and asked to find average velocity, then that's just asking us to find the average value of the function. Okay, so the way we would calculate that, the average velocity would be 1 over the length of our interval, b minus a, times the integral from a to b of my velocity function v of t, which we're integrating with respect to t. Now let's see if those units make sense. Okay, so if we see the resulting units that's going to take place with this calculation, we would multiply the unit of measure for velocity times the unit of measure for time, so that would be meters per second times seconds, which means that that integral would give me something written in terms of meters, but then we are dividing out front by something in terms of seconds. So we're going to get a calculation that is in terms of meters per second. So this also gives us average velocity. And if we look at first glance here, these two average velocity calculations look completely different. But believe it or not, they're exactly the same, because if we take the integral here, so the integral from a to b of the velocity function, that's going to be the position at b minus the position at a, and then we're going to divide that by b minus a. So these two things actually wind up computing the same quantity. They compute the average velocity. They look different, but when you manipulate that average value formula, in this particular case, it and the average rate of change are exactly the same. Okay, So just one for you guys to practice. If I gave you a velocity function and asked you to calculate average acceleration on the closed interval from A to B, what are we going to use here? Average value or average rate of change? And because acceleration is the rate of change of the function that we are given, we're going to use average rate of change here. So this would be V of B minus V of A all over B minus A. And again, average rate of change gives us the slope of the secant line containing the endpoints. Okay, so again, like what we talked about at the very end of the lesson, like that stuff is going to be super useful for us whenever we are working through rates-free response questions. Okay, so we'll talk more about that in class this week. And I hope you guys had a great weekend, and we'll see you on Monday. Take care.